Hello, hi everyone. So this video is meant to be a short guide to using Simulink to simulate electrical circuits for electrical engineering undergrads. So let's start. So the first thing you see in Simulink, or the first important aspect of Simulink, is the library browser. That's where you get most of your components, most of your electrical components, and for most of what you're going to be doing, these few components that I have out here, these blocks, are basically what you're going to need for for most of what you're going to be doing on Simulink, especially if you're maybe in your first year or your second year. So to get components from your library browser, you just search the name of the components. So let's say I want to get a current source, just current source, and when I search, so it will search. As you can see, I'm using MATLAB online, so it might be a little bit slow compared to running the desktop version. So if you're using MATLAB online, it's preferable that you have a very good and stable internet connection, okay, to avoid any inconvenience. So I can get the blocks. Yeah, the current current source rather, is right here. Yeah. That's an AC current source. For this, we're going to be dealing with a DC current source. So we are going to be simulating some very basic RLC circuits. So for example, we'll simulate this. We're expected to get this kind of output for the voltage of the capacitor, and we'll also simulate this circuit using the same input we used there, and we're expected to get the same value we're expected to get this graph using that same input that's just a pulse from at 0 of 12 volts that lasts for 2 seconds and dies down. So that's what we have for today, so let's get into it. So as I alluded to earlier, the most important thing in Simulink are your components. So I'm going to just walk you through the basic components you are going to need for most simulations. So this is your display. You use your display when you are trying to output like discrete values. Let's say you have a voltage sensor connected in parallel to a resistor. When you run the simulation and you want to see the output of that voltage sensor, you connect the arrow tip here that you see here that I'm hovering over. You connect that arrow tip directly to the display, and on the display you will find the value after the simulation has been run. The next important component is your switch. So your switch controls flow of current in your circuit. So you can have a circuit without any switch, or you can have circuits with switches. This particular switch is going to be driven by a physical signal. So you can see PS, so that stands for physical signals. So there are different kinds of signals in Simulink. So you have physical signals, and you also have Simulink signals. So we also so that brings us to this component. So this particular component, yeah, this one here, is a Simulink to PS converter. So let's say you have a Simulink signal, yeah, so that's the block parameters, sorry. So let's say you have a Simulink signal being outputted by some part of your circuit or some part of your simulation. What you do is that you connect that Simulink sensor, or the Simulink signal rather, to that before you connect it to something like a display, or before you connect it to another component that requires a physical signal. So you use it to switch between a Simulink signal and a physical signal. And this, on the other hand, is a PS to Simulink signal. So you use it to switch from a physical signal to a Simulink signal. Over here we have this block. This is a scope, the abbreviated or shortened version of an oscilloscope. So you use this when you are looking for waveforms. As you can see, there's nothing connected to the oscilloscope, so there is no graph here. So for those two problems we are going to be tackling today, we're actually going to be making use of the scope, not the display. But we would do just a single problem, just to simulate a single circuit, just to show how the display works. But for the two problems here and here, you can see we're expecting a waveform, a graph. So we are definitely going to use the oscilloscope or the scope. Yeah. Here is your inductor. So your inductor, you can vary the parameters when you just double tap. On the inductor, you have the block parameter window show, so you can adjust the inductance. So we're going to be needing this a lot too. We also have a resistor, same as the inductor. You can double tap, adjust the parameters, change the resistance value. It's measured in ohms, so you can just do that. You also have a capacitor. You can just double tap this also. The block parameter window should show, and yes, exactly, so you should be able to change the values. Yeah, so that's that. Okay, so whenever you want to measure maybe current or voltage across a particular component, you're going to make use of a current sensor. So a current sensor works typically in the same way your ammeter works. So you connect a current sensor in series with the rest of your circuit, or in that branch, so that you can measure the current flowing through that branch. But your voltage sensor, you connect it in parallel with the electrical component, so you can measure the voltage across that particular component. This is a very, very important component. It's called your solver configuration. So this is actually what Simulink uses to solve the unknown equations and give you the values for your current and your voltage. So for every circuit, you must connect a solver configuration block. If you do not, your answer will not converge, meaning that it will not get an answer, so you won't be able to get the values. We have this pulse generator. So this pulse generator, you can double tap on it. More on that later, by the way. We'll talk more on the pulse generator later, but we're going to use it to simulate. We're going to use it to control this switch here, because the pulse generator outputs a physical signal, so we can mimic the effect of a switch being closed or open. So if a pulse is at its highest value, its peak value, maybe a value maximum amplitude of 1, that will simulate the circuit being closed, and when it is on 0, that will simulate the circuit being opened. So that's how we can use this pulse generator to control a switch, and we can just vary the parameters of the pulses. We can change the duration of each pulse, we can delay each pulse, and just do a lot of other things with the pulse. So this is your de facto, this is your DC current source. When you're working with DC, it is advisable to make use of, although there's a generic current source block, but when you're using DC, it is advisable that you go with the DC current source block. Just makes everything simpler. And we also have our electrical reference. Yes, also without your electrical reference, your solution will not converge, so you won't be able to. MATLAB will not arrive at, sorry, not MATLAB, Simulink. Well, but they are under each other, but Simulink will not arrive at an answer if you do not have an electrical reference. So I think we've covered basically everything. Yeah, so we're done. So let's just do a very simple circuit that will demonstrate the voltage divider rule. So that's let's say, so let me duplicate this. Okay. Oh, sorry. Let me just duplicate this. Yep. Okay. Yeah. Okay. So let's move this over here. So we've moved that over there. Let's just have two resistors. So the current divider rule states that the current, the voltage divider rule, which is what we're trying to verify in this simple circuit, states that the voltage is proportionally distributed across resistors connected in series proportionally with their magnitude. So yeah, so let's do that. Control V. Okay, so we have one resistor. One resistor, sorry about that. One resistor, another resistor should be here. Yeah, and that's our second resistor. So that's our second resistor over here. That's the second resistor. Okay, so as always, we need to have a solver configuration. So let me go ahead and copy this. So it's very important to have a very stable and fast internet connection. So as you can see, my it lags quite a bit if your internet connection is not really so great. Okay. Oh wow, yeah. So let's do this again. Alright, so sorry, we're back. So we have all the components for this circuit out. So whenever you want to make a connection, you just drag from like the end node to another element. So you can see it's showing you, those arrows show you possible combinations, so what can connect to what and so on and so forth. So yes, so it's just as simple as from here to here. Yeah, that's how simple it is to make a connection. Yeah, that is connected, and let's just complete the circuit this way. Make a connection here. Yep, just here, and that's that. So let's take the solver configuration. As I said, you must always have a solver configuration. Okay, so the solver configuration, okay, we have a solver configuration there, we have an electrical reference here. Okay, so now we can also do the same, just connect the electrical reference to the circuit, yeah, and connect the solver configuration to the circuit too. So that is that. So all that's left to do is to add our voltage sources. So remember, we are validating the voltage divider rule, so we need to have two voltage sources. So let's say this is going to be 10 ohms, this is going to be 5 ohms, or no, let's make it 6 ohms, and this is going to be 7 ohms. So that is what we are going to be using for this simulation. So let's just copy this voltage sensor, Ctrl C, take our voltage sensor over here. Let's just place him here. Here's fine. Yeah. Now we have another one. So let's just place him here as well. Let's place him here as well. Let's place him here. Okay. So we have our 2 voltage sensors. So all that's left to do is to connect the voltage sensor. So once we select the voltage sensor, yeah, you just use Ctrl R to rotate. So I want to rotate it such that it's easier to connect positive to negative terminals of this resistor. We connect the positive terminal here, negative terminal here, and also do the same for this resistor. So that is what we're trying to do now. And for this one, we do the same. Rotate, 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 and we're good. Yeah. So we also need another display for the output of this. Okay. Okay. So we need this over here. Yeah, that's where we need. So we connect, as I said, we connect the leads here. So as you can see, something is wrong because this line doesn't turn blue. It's a dotted line, so that's telling you that, oh, this connection can't be made, or it's basically Simulink telling you this connection is not legal. So that's basically what it means. So let's move this down a bit more. Let's take it down a little bit. Yeah. Okay, that's fine. So this particular block outputs a physical signal. So we're going to need a physical signal to Simulink converter to make this connection legal. So to make it work, so I guess that is PS to Simulink converter. So we're going to need this. So copy that. Copy that. Take it over here. Oh, sorry, that made a connection. Let's undo that, please. I made a connection. So, yeah, that made a connection. We didn't want it to make a connection, so we just wanted to move it. Okay. So you take the block, move it over here. Yeah. And we rotate. We move to the side. And to delete a connection, you just select and you delete. Yeah, select the connection. So we selected that connection and we deleted it. So as you can see, this connection, yeah, it's showing that it can work. So it did work. And from here, you just go here and drag it. As you can see, connects perfectly with the display. So we're just going to do the same thing with this, but we're going to rotate this guy a little bit. So, no need for rotating. Let's just leave it this way. So after rotating, let's connect this first to the resistor. So positive to positive, negative to negative. I'm just connecting him here. Yeah, perfect. That's good. So let's do the same here. Positive to positive. Okay, no, that was not correct. Okay. And from here we just connect all the way down here. Connect all the way down there. So that's fine. So we also need PS to Simulink converter, so let's paste one of that. One of those. Control R to rotate. Okay, now that was selecting a connection. Control R. So we make a connection from this output here. So after connecting, this is what we have. So now let's modify the parameters. So double tapped on this, the window should open. So we see it's 1 volt. Let's make that 10. So 10 volts. That's 10 volts. So it applies. Let's make this first resistor 6 ohms. That's 6 ohms. And let's make the second one. Let's make it 4 ohms. So as I've said before, if you're using MATLAB online, make sure your internet connection is stable and very fast. So 4. As you can see, if it's not so great, it might be a little bit laggy and mildly annoying. So we're done. Let's save this, because when you're using MATLAB online, you just have to be sure that you're saving every single change you make, so that in case your network goes down, your work is still saved. So that's fine. So let's run. Compiling. Yeah, okay. So as you can see, this is 6 ohms. So that is 6 ohms, and this is 4 ohms, and this is 4 ohms, and this is 10 volts. So from the voltage divider theorem, the voltage across the 6 ohm resistor is going to be the 6 ohm resistor 6 divided by the equivalent resistance, which is 10. So 6 over 10 times 10, which is the source voltage, and that's 6. So 6 volts as expected. Here too we have 4 divided by 10 times 10, and that is 4 volts. So you use the displays when you want to get like a value but not a waveform. So if you want to get like a waveform, your best bet is your scope. So that's good. Let's simulate this other circuit. So when we look at this circuit, what do we have? We have a voltage source, which is just a pulse of 12 volts that lasts for 2 seconds. Then resistors, 260 ohm resistors, one 3 Henry capacitor, and 1/27 farad, a 1/27 farad capacitor. No, that's the capacitor, this is the resistor. Yeah. So This problem was designed, or you were intended to solve this problem with PSpice, but we're just going to solve it using MATLAB or Simulink instead of PSpice. So going back here, let's clear what we have so far. Select all and delete. So we've cleared what was on the screen. Let's have another circuit. So we are going to be building this circuit. As I said before, it was meant for PSpice. So what we can do is that thinking through this problem, this is just saying you have the equivalent of a switch here. So we can put a switch here controlled by a pulse that only lasts for 2 seconds, then dies immediately after. So that's what we're going to do. And by default, your simulation lasts for 10 seconds. Yes, for 10 seconds. So it's here. You can change parameters. If you want your simulation to last longer, you can just modify this, maybe 40 seconds or so. So we still have our electrical reference, our solver configuration untouched because we're going to need them. So let's get a voltage source again. So we're copying a switch now. So we have a switch. All that's left is we need 2 resistors. Okay, 2 resistors. From here, put one here. We put another one here. Just move that. We move this too. Okay. So we move this. So moving this voltage source down a bit, and we move this guy down a little bit. So I find it's much easier to control this with your keyboard arrows. Yeah, it's much easier to control it that way. And this is supposed to be in parallel, so let's fix that. So Control R again to rotate. So okay, now we shift this way. We shift this way. Yeah, we have it where we want it to be. Okay, so this is what we do. Let's add a capacitor. Ctrl C, Ctrl V, Ctrl R, move it up a bit. So looking back, okay, then we just need an inductor. Ctrl C, and so remember how I said that we could use this pulse generator to control this switch? So that's exactly what we're going to do. So we're going to take one of this and Control V. Yeah. So let's take the leads from here and just connect it with this. Okay, it's lagging a little bit. Okay. This, if your internet is not stable, it does like this a whole lot of times. So yeah, we're back. We save to avoid losing all our work. Situations like that. So that's that. Okay, I don't think it's saved. So let's try saving again. I'm just going to select this lead. Okay. Okay, this is clearly not working. So I guess we're going to have to use a converter instead. So let's get one of these. So I think we need a PS. So we have a Simulink signal, yes. So we need to convert it to a physical signal. So let's copy one of that and paste it. Just move it here. Move it a little bit. Fine. So we connect this to here. Yeah, that works. And we connect this to this. And that also works. So we've connected that. So let's connect this here. Connect this to this. Connect this to this. connect this to this circuit, to the battery, and connect this way, connect it all the way to the capacitor. Connect this resistor down, and we just finish up the connections here, and it's looking like this circuit already. See, it's looking like that. So let's start modifying the parameters. This was 3 henries. This was 60 ohms. This too was 60 ohms. So this capacitor, okay, so that's that. So remember the value of the capacitor, 1/27 farads. So let's do that. Close that. So in the problem they asked us to display the voltage of the voltage across the capacitor. So they asked us to graph the voltage across the capacitor, and that's exactly what we're going to do with the scope. So we need to modify this value. So okay. So just in case, let's just save. Now we can change the value. 1 divided by 27. That will automatically change the value of the capacitance. So before we continue, we have to connect this solver configuration and connect this electrical reference. Okay, so in this question, what was graphed was V of t, that's the voltage across the capacitor. So we're going to need a voltage sensor to measure the voltage across that capacitor. So copying this, and we'll paste it over here. So we have it there. So we just make the connection positive to positive. Positive to positive. And negative to negative. So that's what we're doing here. Okay, we're nearly done. So let's get a scope since we're going to be looking at the waveform. So let's get a scope. Let's connect. Let's move this down. Now let's see if this would work. If we click on this, can we connect to the scope? You see these blue arrows that pop up whenever you click on a point? That's telling you where you can connect to, meaning we can connect to here, we can connect here, we can connect there, but sadly we don't see a blue arrow coming out here, meaning we can't connect to the scope directly. So we're going to need a PS to Simulink converter here. I guess that's this. Yeah, PS to Simulink. I'm going to copy that, paste it over here. Then when we click on that port, you can see it connects here nicely. So we just connect it to here. And this will be able to connect and dock with this. So let's connect this. Okay. Yep. Make that connection. And I come here, so you can just tap on these blue arrows. Yeah. To make it easier. Yes. So that has been connected successfully. So we need to change the parameter for the DC voltage source. We're going to change it to 12 volts. 12 according to the question. 12 volts. Oh wow. So that is probably my internet. So let me fix that. Okay, it's back. It's back. It's back. Okay, so that's a warning sign to save. Okay, that's it. So now the slightly more complicated part. So we're going to be using this pulse generator to control this. But before we do that, I also want to get another scope there so I can monitor the output from the pulse generator. So Ctrl C, paste it over here. Oh no, we are not creating any annotations. So we have that here. So we just move it up. And remember, this is a physical signal, so I don't think we're going to have any problem. This is a Simulink signal, so I don't think we're going to have any problem connecting this here. So let's just try go ahead and connect that here. Did that work? Yes, it works perfectly. Because this is outputting a Simulink signal and this receives a Simulink signal, so just connect. It's important to connect it before you pass it through the Simulink to physical signal connector, because on this other side it is now a physical signal and a Simulink signal, so you have to put another one of these, which is a Simulink to PS signal converter, or PS to Simulink rather, to convert this to a Simulink signal, then you can look at it. So let's modify the parameters for the pulse that we're going to create. So we want our pulse to last for 2 seconds. So going back here, let's just see, just 2 seconds, a 2-second pulse. Okay, so how can we frame this in this context? So I guess we can maybe change the period to maybe 2 seconds or 4 seconds rather. Or no, let's not make it 4. Let's make it 2 seconds. Yes, let's make it 2 seconds and make the period 100%. Pulse 100% of the period. So 100%. The period. Or we could make it 4 seconds and let's look at this. Let's go with this. Okay. Okay. So it seems like there's a problem. So I may just have to put it back to 10. Pulse width shouldn't be 100%. So let's say 90 pulse width. I want it to be for 2 seconds. So we just want. Let's not use simulation time. Okay, let's use simulation time. So we'll shorten the simulation time to 4 seconds. Then we make it 50%. Okay. Okay. So let's just change this to 2. Or let's be 4. 4 rather. 4. So let's run this simulation. Let's save, then run. So it's done saving, so let's run the simulation. So remember we have a solar configuration and electrical ground there. So it's done compiling. So you double tap on your scope to see the signal. So let's see how our pulse is. So it was on all through. It was on all through. So let's find a way to make this be at 1. Maybe start from 0, be at 1, then come back down. So at 2, so that's 50% of the total period. Period is 4 seconds, so let's make that 50% of the total period. Okay. So we'll come back here. Okay. Period should not be 10 seconds. Let's make the period 4 seconds. Make the width 50% of the period. Okay, let's see. Hopefully this should work. Okay, so I guess this is, and just do this off. So I think this worked. So let's, yeah, it worked. So let's close this. So that should work for only 2 seconds. Since the total period is 4 seconds, we said the pulse width should be 50% of the total period, that's 2 seconds. So let's see. Of course, you could have made your simulation last for 10 seconds. Then you make your pulse with last 20% of the second, 20%, but because it outputs like regular pulses at a certain time, it is going to create another pulse. I don't want that, so that's why I'm using 4 seconds. Okay, so let's just close this. We save again. So that's my internet. Okay, we're back. We're back. So we save. And we run the simulation. It's compiling and it's done. So let's just look at the scope just to make sure that we had the correct value or the correct pulse. Okay? Perfect. So it just goes down, and you see it goes down, exactly goes down. Although it does spike at the end, but this will be something you see towards the end, but not really. So let's close this. Let's look at the signal that we got. Yeah, as you can see, that signal is in fact what was expected. See, it picks about a little bit over 4 volts, and this is, yeah, close to 5 volts, yes, close to 5 volts, because this, wow, perfect, spot on. This is exactly what we're expecting, and this is what we had. Yeah. So I would call that a success. Yeah, 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 it is. So yeah, that is correct. So after 4 seconds, oh, coincidentally, I didn't even see that here. The same rationale we used, rather, they used 4 seconds, and we also used 4 seconds. So I didn't even see that. Wow, that is nice. So yes, so hopefully this helps you um, grasp simulating circuits with Simulink, and yeah, good luck.